All right, so this is total internal reflection, and this is everything I've done in one screencast. Where in the past you gave me a two, and I did a different problem and got another two, and I want I want not a two, so I want to. So I did everything in this screencast here, or I'm going to. So this is the first problem. Has to do this is the diamond, and the versus the quartz, and they have different indices of refraction, quartz and diamond, and so you're calculating how much um, uh, of each light gets from A to B. And I'll give you, not to blow the punchline, but with the quartz, it's not very much. But so let's see what happens mathematically. Here we go. Okay, so 3/8. Okay, Ni. So the index refraction of the quartz is, or the not the quartz, so the diamond is 2.42, and the the N of the air is 1. So first I calculated the critical angle using that formula, and I got 24.4 degrees. I just converted from radians to degrees. So anything above that will have 100% transmission. The only place where we'll have transmission, according to this diagram, everything is above that except for the exit, which it needs to. Oops, that's my grades. You probably don't need a reminder about those. All right. So where am I back? Okay, there we go. So then first I had to calculate all I need to do is calculate so all I had to do was calculate the transmittance for D, the P transmittance, because that's all they asked for, and that's the equation right there. That's the Fresnel equation for P, what do we get? Is we get transmittance is 1.799, and it really doesn't mean a whole lot until we actually get the all right, well, that's just the Fresnel coefficient. This is the transmittance, where we take the Fresnel coefficient squared. And that's 93% for diamond, so that's pretty darn good. Now for quartz, we did the same or I did the same process, not we. And I got angle is, this time the critical angle is 43 degrees, so there's a much larger. And if we go back to the original picture here, let's find that. We go back to the optics book. There we go. Oops, that's not it. That's something else. There we go. Okay, so um, okay, so 43. So that's going to have some loss there. That's not, but that will, and then that will as expected. So 100% will reflect there, but not there. So that's different this time. So let's do some math now. Back to this. Okay, so we've so okay, so we got so critical angle. Um, so first what I did is I calculated so our first angle was obviously. All right, what I did here was I calculated at the exit again. So it's the same angle, that 18-degree angle. So I went through that. I just changed the indices of refraction. The only thing that changes actually in that calculation is the index of refraction of quartz. In this case, 97% of the light leaves it going through that whole process again, that's good, because we want lots of light there. But where we have the problem is at this 40-degree. Oh, wrong one. Let's close that out. But we want the is at that. We watch reflect there, though, at that 40-degree angle. So let's see what happens. Let's go back to Mathematica. There we go. So I've put in a new angle, 40.5 degrees. I calculate the arc sine, the angle of what that is, and it's 1.2 radians, and that is like 70 some degrees. And then I get the Fresnel coefficient of transmittance, and that's 1.81. And then excuse me, then the transmittance value is 94% is transmitted into the air. So that means only 5% stays of the light. If you multiply the 5% times the light that was transmitted at the exit, we end up with only 5.72% of the light is transmitted to point B. The rest is lost elsewhere. So that's not very good. So that's how you can tell it's a fake, is if you don't have much light shimmering from that point there on the top, I guess. So anyway, now, oops, back to my grades. We want to avoid those for now. Okay, the next question had to do with evanescent waves. And that was kind of tricky, but it was just basically there's a relationship here that I learned all about between, let's go in the textbook here. There's kind of a cool section about that right there. But basically, so you got the incident waves and then the evanescent waves when there is total internal reflection. It creates these okay, there's not a really good picture here, but they're parallel now to the interface, and they decay very quickly, and that's where calculating is the decay of the evanescent wave. So let's go back now to the Mathematica, and we're looking at where is the amplitude equal to the value of 1 over e. Now, we know that we learned in class back a long time ago that the evanescent wave increases at a magnitude of e to the negative y over z. So y is the interface axis, and then z is the distance from the interface. Okay, so that is the ratio at which it decreases, and we want to know when 1 over e, so that means y over z has to equal 1. So actually, anyway, so we can say that we know that 1 over z equals that. So we can just substitute that in for our value of into the equation, and I did that right there. Our initial angle is 45 degrees. Our n1 is 1.5. Our n2 is 1. So then y just equals 1 over all of that. I did that, and oh, by the way, 500 nanometers. I just use that. So keep units consistent. Our amplitude will be 1 over e at 225 nanometers. So not very far, and it's expected that that length should be less than a wavelength. So that looks pretty good there. 315. We're looking at reflection through metal. Now in our textbook, we're doing Fresnel coefficients for this problem. It's just that, however, it's just that if we do them as they rewrite the equations to make this a little bit more doable, and I'll show you where. But first of all, this is silver. Our index of refraction is 0.13 plus for I, and our value of our angle incident is 80 degrees or 4 pi over 9 radians. Not that mattered. And anyway, so the book, it gives us this equation. Yeah, rewrite some, which is nice because it kind of helps us deal with by squaring. It helps us deal with the imaginary numbers, but not really actually, because I guess we can if we were doing this by pen and paper, it would help because we could assume that the imaginary part, that when you factor out that is about 0, so you can just kind of throw it out. But we have Mathematica. But anyway, and there still is an imaginary part. So that's why I had to do all the real, because we don't see the imaginary. So our RS is negative 0.9 0.99. Our RP is 0.36. And then I had to put in that crazy form with phase shift. But what was cool, and I was so like confused. Like, what is the world is phase shift? And fortunately, there's this little chart here. And that's cool. So at 80 degrees, our phase shift of our P is about negative zero point 0.5 pi radians, and at in our S it looks like it's about negative pi. So I just went with that. There's probably a way to calculate that out more mathematically than looking at that chart, but that's what I had, and that was the simplest to do. So I'm going with RS equals 0.9939 e to the negative 5 pi, and RP equals 0.3626 e to the negative pi. So that is total internal reflection.